So last time we talked about binary search tree, how we can construct such a data structure in R, as well as to find the height of a tree. So we first use this R6 reference class, and then we define a node, which consists of the node value, and then a left child, and then a right child. So this is a class for a node. Then we also define a class for the binary search tree, short for BST, and it has a root as its basic elements, and we define an insert function. So basically, we want to insert arbitrary value into this tree, and then to its corresponding or its correct position. And it also involve a recursive function, and this recursive function will be like if a specific node is already occupied, then we, based on the value, we go down one level deeper, and then we put the data at the corresponding at the correct position, but it need to be done recursively. So we also define this insert recursive, so that we keep going down into the tree, and then we locate the position, and then we put the value at its corresponding position. So that's what we did last time. And next, and we also have this get height function. Basically, it's to get the height of a tree. And so today we will be working on, first is to search for a node, and this function will have a input of a data and a current node. So what it does is that inside this binary search tree, I want to, or given a particular node, for example, like given a root of a tree, we want to see that if this data is inside this particular, if it exists in this tree. So basically, binary search tree is a way to store data, and this is just another function that we can get we can check if the data is located in this so-called data frame or data structure. So to search for a particular value. Okay, so and again, it is going to be a recursive function. So we also need some condition to exit this recursive call. So one is that if is null for this current node, that means basically value not exist in tree. Because at the end of our search in this implementation, at the very end, if we reach a node that it still give us a no value and it does not exist, because this is going to be recursive, and we will keep going down until we search or find it or not find it. So if in the last step we still get a no value, so there's no such node, we still get an empty node. That means that the value that we're looking for does not exist. And then else if, and this will be the condition that we found the value. So data is equal to the current node, the value of a current node. So current node will always be a node classes, as what we defined last time, and then this value will be the value of this node. So if the data equal to that, that means we found it. So we can just print value found. And this is just the two cases where whether we found it or not found it. But what about if we are in the middle of a tree? So we need to define the recursive part. So else if data is less than the current node value. So that means the data that we are about to look for is going to be at the right hand side of the current node. So it will be the left subtree. So we will first call the self, and then search for node. We call ourself again, and then data, which is fixed. This is the part that we are keep looking for, but this time we know that it will exist at the left subtree, so we want to search for the left. And finally, else if data is greater than the current value, then we call our function again, but this time we search for the right hand side, right subtree, because we know that the data is greater than the value of our current node, our current location. And then if still going to if the data is still greater than this part, then we this value, then we are going for sure we are going to the right hand side, the right subtree, and then to search if in the right subtree this value is exists or not. And once we enter the corresponding subtree, then we will run it again, and then we will keep checking, and then we'll see if value exists or not exists. So only this two part will cover the recursive part, and then this two condition will cover the whether we found it or not found it. And since it's a recursive function, we need a exit condition here. So this will serve as our search for node. And yeah, so this is one example or one implementation that we are going to do in this example. And for the next one is about deleting the tree. Yeah. So we will call delete. And yeah, don't forget the comma here, and also we are still in the list, so we need an equal sign here. So it's a function. Again, we are deleting for we are going to delete a particular value. So this is the value that we first need to check if it exists in the tree, and then if it exists, then we want to delete that particular value from our current tree. And here we also need to give a current node, and we can just give in the implementation we can just give we can just use the root as our or any nodes, but for example we want to talk about the entire tree, we'll just give a input argument as the root. Okay, so now to delete, it will also going to be a recursive function. So now we will check one of the exit condition. So again, if no, then just print no such value for deletion. This is the part where we exit the recursive function, and when yeah, because we will keep searching, because our first step is to search if this value exists in the tree or not, and then we will perform the deletion. So if at the end of our searching we still does not find this value, or we reach an empty node, then for sure that there's no this value in this tree, so there's no such value for deletion. And then else if. So again, we are going to check if data is less than the current node val, then so this data is smaller than that, so we need to perform our deletion at the for all the left subtree. So our current node left is going to be replaced by the output of the delete function. So this part is the part where we call ourselves again and perform recursive implementation. So delete data, but we are talking about the left subtree. So we want to replace our current node, the left node of the current node, with the output from the deletion. And then the deletion, the input, will be the left subtree, or the node from, or the root of the left subtree. Similarly, if this is greater than, we will replace the right subtree with the output of the deletion. But the deletion is also talking about the right subtree. And finally, for the else cases, so this is no such value for deletion. This is that we are going to work on the left subtree, and this part is that we are going to work on the right subtree. So, or we are going to, the things that we're going to delete is in the left subtree, or the things we are going to delete is in the right subtree. And the else cases will be, actually it's value found and perform deletion. Okay, so in this case, we are also going to talk about different possible cases for working on the deletion. So case 1 will be no leaf node. So if is null that current node dot left and is no current node right. So both of them are no value. That means there's no leaf or no child node. So we can just let our current node equal to no value here. So I think this can be given, we can see it from here. So for example, the part we want to delete is 7, which corresponds to no leaf child. So what we did, we just delete the 7, replace that as a null, and then that will give us our resulting tree, the one that we delete the leaf nodes. So basically we just replace the leaf node as no value. So that's our case 1. So when both of them are null, we just simply replace the current node as null as well. And this is case 1. And then for case 2, maybe let me put this inside the parenthesis. So this outer else condition is that value found, and then we are going to perform deletion. But deletion also comes with different condition, and this is the part where we are inside the outer else. We are going to do some checking as well. So yeah, and then another else if, and then finally another else. So this will be our basic structure, and our else if, the first else if will be a case 2. Say either maybe no left, and then this is also a case 2, and it is a no right. And finally a case 3 is that just a regular node. It has left and right child. Okay, so if no left, that means we need to check is node current node left. Okay, then if no left, let's see if we have an example of that. Okay, yeah, so here, this one does not have a left child, but it has a right child. So what we need to do is just, we can simply replace this 6 with this 7. So we remove 6 and then bring all its right subtree just one level up. So we just replace 6 with 7. If there's anything following or below 7, it will still carry up. It will still remain, but it just push one level up. So that's because there's nothing at all on the left hand side. So we just push the 7 all the way up one level, removing 6. So here we just current node itself equal to current node right. And our bottom line is that we still want to remain we want the property to remain that the right child is greater than your parent value, your left child is smaller than your parent value. So this is the only condition we want to met. And yeah, so by doing so, we will be able to remain this property here. So again, our second condition, if there's no right child, that will be this case. So there's no right child, but we want to remove 2. So we just basically remove 2 and then push this one level up. And if there's anything following the right, if there's a child node for level 1, for this one here, everything will just be pushed one level up. Because there's no nodes on the right hand side, so we have nothing to worry about for that. We just remove that and then concatenate this one to push one level up. So yeah, so these two cases are basically the same. We just because they're also two simple condition. If one node is missing, then we can just directly push one level up by removing the current nodes. So yeah, so our last condition is that, yeah, because a node can have either one of the 3 conditions: no leaf, and no left, or no right. So 0 child, 1 child, and 2 children. So this is the case that we need to put more effort on to work on that. So that will be the cases like, for example, 5, and it has both child here. So to do that, what we need to recognize is that, for example, we want to delete 5. Actually, there are many ways to perform this kind of deletion, and the one that we are going to use is that we are going to replace the smallest left value, the smallest value in the left subtree, and then we're going to replace the value that we want to delete with that smallest value of the left subtree, and then we will remain whatever on the right hand side. So for example, we want to delete 5 here. Oh no, sorry. We want to replace with the smallest value of the right subtree. So as for example in here, we want to delete 5. What we need is the subtree, the smallest value of the right subtree. So that will be 6 here. So we remove 5 and replace with 6, which is here, and the 4 remain under this part, but except this is going to be a 6, and the 7 is going to push one level up, and whatever is remaining will stay the same. So what we are doing here is that we are actually trying to preserve the property that the left value is smaller than your node, your parent node, and your right is still going to be greater than your parent node. So in order to do that, we can only find, or in this example, we are going to use the smallest value on the right subtree to replace with the current value. So 6 replace 5, and the 4 and the 7. So its original left and right subtree remain the same. And in this case, the property that 4 is less than parent node and 7 is greater than parent node is remain. So again, so say we want to delete this current node, we are going to first search for the smallest value of its right subtree, which is 6 here, replace the value that we want to delete with 6, and everything else remain or push one level up, and that will be our performance. So first, define a temp, and here we have a find min function. This is a function that we haven't defined yet, so we are going to do that later. So find min, something we will define later. Okay, so as if we have them for now. So find the min of your find the minimum of the right subtree of the current node. Okay, then we replace the current node value with the node that we found and that value. So for example, want to replace this 5 with the minimum of its right subtree, which is 6, and then replace 5 with 6. So this is the part we replace. And finally, our current node right. So because these two steps are only replacing the value, but after we replace, the 6 still remain in the right subtree, so it will be 6 and 6 and 7. So now we want to remove the 6. So again, we want to perform deletion for the right subtree. So self and delete, and what we want is just we want to delete 6 now. We no longer delete 5 because 5 is already replaced. So now we want to, which is replaced by 6, and this is now we want to delete from the right subtree. I want to delete the 6. So once again, so we replace this 5 with 6, and then we delete this 6 and then make it as 7. So we delete that, and then the 7 will, so it will just becomes a case 2 where there's no left child, so the 7 will be pushed one level up, and that case is already been taken care of, case 2 and case 3. So we can just directly call the delete function, and then it will perform delete the one for replacement. So we don't need to do extra step because this part, it becomes a case 2. So it will be taking care of these two else if. So yeah, so this will conclude our deletion function here. So yeah, so we do a search for node and delete, and we missing one find min. Okay, yeah, so the very last part is that we want to find the minimum. This is that we want to find the value for replacement. So again, it will return takes a current node as a position, and it will again be a recursive function. So if is dot no value, let's see, yeah, so if the left child of the current node is a empty node, that means we basically found the smallest value because there's no other value that is smaller than the current node val, because again, the left must be less than the current node val. So if the left becomes an empty, that means the current node val is the smallest value in the right subtree. So we just return current node, and then else. That means we still haven't reached the left outermost the left so there's still value in the left subtree. That means we are yet finding the minimum. So we return. So we keep searching. So self find min, and then we keep searching the current node left, because the smallest value will always be the left hand side. It's because the left will always be smaller than your current parent node. So we keep searching the left node until we reach the bottom, that there's no more left nodes for that node, and that node will have the value that is smallest in the subtree that we're searching for. And in this case, it will be the right subtree. Yeah. So again, just to summarize, we do a search for node. It will return whether it exists or not exists. If and then otherwise keep searching. It's right or right. There's a typo here. Keep searching for the correct position based on the value, whether it's larger and smaller than. And yeah, and then for deletion, we also first based on the value, keep searching for the corresponding position that we want to, that we first find the node. Once we find it, and then we are going to delete. So this three part is for finding the node, and the last one is that we found it, and then we are going to perform deletion. And the deletion also come with three different cases: no child, or one child, and then both child. And then we're going to do that. One tricky part is that we want to this part. So make sure you pause the video and make sure you follow the logic here. And you can use the example, or these two example, to think about what we are doing for case 3. Last part, we need a supplement additional function for finding the mean. And this is what we define here. Okay, so now we have everything. Now we just do an experiment for testing. The node class and the binary search tree class. We use our previous example here. So we create a tree here. This is the tree that we create. Find the minimum, starting for the root. And as can be seen from here, the minimum, we keep searching on the left hand side, so that should give us a 1. And indeed, this 1 is the minimum of this tree, so we should get a 1 here. So let's take a look. Yes, it gives us a node, and the value is the node with value 1 here. So okay, that means our find minimum is working. It returned the correct number, the correct minimum. Okay, so now let's test for the search for node. We start from the root, so basically we want to search the entire tree, and we are looking for the value 5. And yep, value found. So that means a 5 exists in our tree. And now let's delete the node 5, and this will be the second example. If we delete 5, we replace 5 with the smallest value of its right subtree, that will be a 6, and then we replace that with a 6, and then we delete everything here and here. Yeah, we end up with a 7, and that is this part here. So what I was doing manually here was what we did in the code here. Yeah, so we are looking for this as our resulting tree. So again, value found, delete 5. Yeah, I think I make a mistake here. Yeah, because this deletion function is going to be a recursive function, and we are going to store the output from the deletion into another object here, so at the corresponding position. So this is the part that we need to return something as the output of the function, so we need to return the current node. Okay, because now we are going to use the output from the delete function, so our delete function should return the node, and that is returning the result to its correct position. Okay, so we need to run the class again. Create a new binary search tree, create a value. The minimum is still going to be 1. Find the value, value found, and then delete value. Okay, it returned a root. So this is just to show us that the deletion is done. Okay, so now we start from here. We expecting a this. So now let's check the root. Maybe just copy paste this part here so that, okay, so the root again is going to be a 3. That's correct. And the right subtree of a root, this should give us 6, not 5 anymore. So we hopefully this should give us 6. Let's take a look. Yep, it returned a 6, and 6 it also have a left child and a right child. So now let's take a look at the corresponding children. So under the 6, the left child of the 6 is the 4, and the 4 has nothing below. So both of them are no. So now, so before 4 is under 5, but now 4 is under 6. That means our deletion is working correctly. And then the right subtree of the 6 is going to be a 7, and then nothing below. So our deletion is working perfectly fine. And after that, we search for 5 again. So in this case, it should return no such value, or value not exist in tree. Yep, because we delete 5, resulting in this, no more 5 and value not exist in tree. Okay, so yeah, we basically done the most complicated situation where there are 2 child, and then we delete that with all those replacement that we just talked about. And now after this part, let's verify one more step, and the result should be this one. Okay, so what we are doing here is that so this is our current tree, our BST here, and we want to delete 6. So okay, in that case, basically we push 7 because we want to use the smallest value of its right subtree, and then with replace to replace that, and then the 7 should be delete because 7 is the only child at the bottom. So it should be this one after we delete 6. Okay, search for 6, value found, because the value is 6 is still going to be in the tree. Now delete 6, and this is what we are hoping for. So delete 6, check for the root. Root is still going to be a 3. Let's take the look at the right subtree of the root. So it should be 7 and not 6 anymore. So yep, it is 7 now. So the right subtree of the root is 7, what we are expecting. And also no more left child for 7. And yeah, before there was no right child for 7, but now as you can see, there's a right child for 7, because with our design, our implementation, 7 is pushed to replace 6, and it has the child 4. And now let's take a look. Yep, the left child for 7 is a 4, and this one should be no. Yeah, so no right child for 7. And finally, let's search for 6 again, and it should be value not exist in tree. Okay, so yeah, in this example, we from last time we have our node and insertion and the binary tree class, and what we did is search for node for searching data in this our new data structure, our tree structure, and then we perform deletion. We have many cases to consider, and we also need a one additional function here for to assist our deletion. Okay, so yeah, Here I also give many example and to verify that. So if you still find it a little bit difficult to follow, maybe you can pause the video and use the example, and then to go over the code step by step instead of just doing recursively. So yeah, thank you very much.